Hey everyone, welcome back. We're always talking about data around here,
Yeah.
but have you ever stopped to think about like the different ways we actually measure the world around us?
That's actually a really important point. It all starts with understanding the building blocks of information,
Right.
variables.
Right, variables like
Mhm.
in math and statistics and stuff.
Exactly. And today we're going to be diving into a really fundamental distinction, the difference between continuous and discrete variables.
Continuous versus discrete.
Yeah, and it might sound a little technical at first, but trust me, this is a concept that really shapes how we analyze everything
Yes.
from, like scientific discoveries to like everyday trends.
Okay, so let's break it down. What exactly are discrete variables?
Well, think of discrete variables as like stepping stones. They take on these distinct separate values with clear gaps between them.
Okay, so like if I'm counting the number of I don't know, books on my shelf, that would be a discrete variable.
Exactly. You can have 5 books or 6 books, but not like 5.73
Yeah.
books.
All right, that makes sense. Each book is a whole unit.
Precisely. Each value is distinct and countable. So like the number of students in a classroom, the results of rolling a die, all classic examples of discrete variables.
Okay, got it. So then what about continuous variables? How are they different?
Well, imagine a smooth flowing line instead of those stepping stones. Continuous variables can take on any value within a given range.
Okay.
So think about measuring height or weight. Theoretically, you could zoom in infinitely and find more and more precise measurements.
Oh, I see. So like I can't have 2.3 books, but I could have a plant that's, like 2.37 inches tall.
Exactly. And with a more precise ruler, you might find it's actually 2.374 inches.
Right, and so on and so on.
There's no gaps between those possible values. Temperature, time, even like the length of a piece of string, these are all continuous
At
variables.
least in theory, right?
In theory, yeah. There are infinite possibilities between any 2 points on that scale.
Okay, so this is making me think about those uncountable noun grammar lessons from way back when. Like I can count the number of grains of sand on a beach. That would be discrete. But the actual amount of sand, well, that's continuous, right?
That's a fantastic analogy, and it really highlights a key point here. The nature of what we're measuring really matters. It dictates the type of variable that we're dealing with, and ultimately influences how we analyze and interpret the data.
So this is already making me see data in a whole new light. I'm wondering, how does this distinction between discrete and continuous variables actually affect how we work with them? Like, how do we measure things like the average or the spread of these different types of data?
That's a great question, and that's where it gets really interesting. Let's delve into the concept of probability and how it plays out differently for discrete and continuous variables. For example, consider rolling a 6-sided die. We know that each face has a probability of 16.
Right. Each outcome is equally likely. But I have a feeling things aren't so straightforward with continuous variables.
You're right. With continuous variables, we can't assign a specific probability to a single exact value. Instead, we think about probabilities in terms of ranges of values.
So if I'm looking at the heights of a group of people, I wouldn't ask what's the probability of someone being exactly 6 feet tall.
Exactly. You might ask, what's the probability of someone's height falling between like 5'10" and 6'2"? And that's where the concept of probability density functions, or PDFs, comes in.
PDFs.
Yeah,
Those sound a bit intimidating. Is that where the calculus comes in?
you're catching on quick. Don't worry, we don't need to dive into the calculus right now. But the basic idea is that PDFs describe the likelihood of a continuous variable falling within a certain range. Think of it visually. The area under the curve of a PDF represents the probability.
Okay. That's starting to make sense. So instead of saying there's a specific chance of someone being exactly 6 feet tall, we're looking at the probability of their height falling within a particular interval. It's like a sliding scale of probabilities rather than fixed points.
Exactly, and this difference in how we approach probability has profound implications for how we analyze and interpret data from different types of variables. It shapes the statistical tools we use and ultimately influences the conclusions that we draw.
This is really eye-opening. We've gone from simple definitions to the fascinating world of probability and PDFs. What's next on our journey into the realm of continuous and discrete variables?
Now that we've touched on probability, let's explore how this distinction between discrete and continuous variables affects how we calculate some key statistical measures.
Okay.
For instance, think about calculating the average of a data set,
The average.
also known as the expected value.
Right. So if I have a bunch of data points, whether they're discrete or continuous, I'd want to know where the center of that data lies.
Yeah.
But I have a feeling it's not as simple as just like adding them all up and dividing.
You're right. It's not always that straightforward.
Okay.
Let's start with discrete variables.
Okay.
To calculate the expected value, we consider each possible value the variable can take on, multiply it by its probability, and then sum up all those products.
So it's kind of like a weighted average.
Yeah.
Where the weights are the probabilities of each value actually occurring.
Precisely.
So going back to our trusty six-sided die example.
Right.
Each face has a value from 1 to 6 each with an equal probability of 1/6.
Yep.
We multiply each value by its probability, add them all up. And that gives us an expected value of 3.5.
Precisely. You got it.
Okay.
Now, with continuous variables, things get a bit more nuanced.
Okay.
We can't just simply sum over an infinite number of possible values.
Right.
That's where integration comes into play.
Ah, calculus.
You're catching on quick.
I knew it was lurking around the corner.
Don't worry. We won't get bogged down in all the technical details.
Okay.
The key idea is that instead of summing, we integrate. We multiply each possible value by its corresponding probability density, given by the PDF, and integrate over the entire range of possible values.
So it's like we're finding the weighted average in both cases.
Yeah.
But with continuous variables, we use integration because we can't sum over an infinite number of discrete values.
Exactly.
Now, let's move on to another important concept, variance.
Variance.
Variance measures how spread out the values are around the mean,
Okay.
giving us a sense of how much the data points tend to deviate from that average.
So a high variance means the data is more spread out, while a low variance means it's clustered more tightly around the mean.
Precisely.
Okay.
And just like with the expected value, the way we calculate variance differs for discrete and continuous variables.
Right.
For discrete variables, we calculate the squared difference between each value and the mean.
Okay.
Multiply that by the probability of that value occurring and sum up all those products.
Okay, so we're essentially finding the average squared deviation from the mean.
Right.
Why do we square the differences, though?
Great question.
Yeah.
We square the differences to avoid the positive and negative deviations canceling each other out.
We're interested in the overall magnitude of the spread, regardless of the direction.
Okay, that makes sense.
So for continuous variables, we'd again use integration instead of summation, right?
Right.
We integrate the squared difference between each possible value and the mean, weighted by the probability density from the PDF over the entire range of possible values.
It's fascinating how the core ideas are the same for both discrete and continuous variables, but the methods of calculation adapt to accommodate the different nature of the data.
It highlights the elegance of mathematics in capturing these fundamental concepts in a way that applies across different types of data.
Right.
And while the calculations might seem abstract, they have profound implications for how we analyze and interpret data in the real world.
Speaking of the real world, I'm curious to see how these concepts play out in different fields.
Sure.
Can you give us some examples?
Absolutely. Let's start with physics.
Physics.
When studying the motion of objects, time is often treated as a continuous variable, allowing us to use calculus and differential equations to model motion with remarkable accuracy.
So by understanding time as a continuous variable, we can unlock these powerful mathematical tools that help us explain and predict how things move.
Right.
What about other fields?
Well, in finance, stock prices are often modeled as continuous variables, fluctuating constantly within a certain range. This allows financial analysts to use tools from stochastic calculus to analyze risk and make investment decisions.
Interesting.
And in fields like biology and medicine, continuous variables are used to track things like blood pressure, heart rate, and concentrations of molecules.
Okay.
Leading to more informed diagnoses, treatments, and overall better healthcare.
Wow, it's amazing how these seemingly abstract mathematical concepts have such concrete and impactful applications in such diverse fields.
Indeed, and understanding this distinction is crucial for anyone who wants to make sense of data and use it to make informed decisions.
Yeah.
Whether you're a scientist, a financial analyst, or simply someone who's curious about the world around us.
Right.
These concepts provide a powerful framework for understanding the information that shapes our lives.
This has been an incredible journey so far, exploring the nuances of discrete and continuous variables.
Yeah.
We've covered their definitions, delved into probability, and even touched on their applications in various fields. What else is there to uncover in this fascinating realm of data analysis? So we've covered so much ground already, from basic definitions to like these really cool applications in all these different fields.
Yeah.
It's clear that understanding, this difference between discrete and continuous variables is like super crucial for anyone who like works with data.
Absolutely.
But are there any common pitfalls or like misconceptions that people should be aware of?
That's a great question. One common misconception is that, just because data is represented numerically,
Okay.
it's automatically a continuous variable.
Okay.
Take shoe sizes, for example.
Shoe sizes.
They're represented with numbers,
Right.
but you can't have a shoe size of 9.32. They still fall into those distinct categories.
Okay.
So shoe sizes are discrete, even though we use numbers to represent them.
That's a good point. It's easy to get caught up in the numbers themselves and forget to consider, like the underlying nature of what we're actually measuring.
Right.
So shoe sizes are discrete, even though they use numbers.
Mm-hmm.
What about something like age?
Age?
We often use decimals to represent age.
Yeah.
Like saying someone is 25.6 years old.
Right.
Does that make it continuous?
That's a tricky one.
Yeah.
While we can express age with decimals for, greater precision,
Mm-hmm.
fundamentally, age increases in these discrete steps.
Okay.
We're either 25 or 26.
Right.
There's no true in-between state.
Yeah.
So even though we might use decimals for convenience, age is ultimately a discrete variable.
Ah, that makes sense.
Uh-huh.
It's like those seemingly continuous variables are actually discrete, but at like a very fine level.
Exactly.
It reminds me of how like digital images are made up of individual pixels, even though they appear smooth and continuous to our eyes.
Yeah, that's a fantastic analogy.
It highlights the importance of understanding like the underlying nature of the data rather than just focusing on its numerical representation.
Absolutely.
This has been an incredibly insightful journey, exploring these nuances of discrete and continuous variables.
Yeah, it has.
We've, explored their definitions, the nuances of probability, and even like common misconceptions.
Right.
But before we wrap up, I wonder if there's anything else that our listeners should keep in mind as they kind of navigate this world of data.
One key takeaway is that while we've focused on this distinction between these two types of variables, there are situations where the lines can blur a bit.
Okay.
Sometimes we might choose to treat a continuous variable as discrete for practical reasons, or vice versa.
Interesting.
It all depends on the specific context and the goals of the analysis.
So there's a bit of flexibility depending on the situation. It sounds like understanding the, underlying concepts is crucial for making these informed decisions about how to actually treat the data.
Absolutely. It's not just about memorizing definitions.
Right.
It's about grasping those fundamental principles and applying them thoughtfully to real-world problems.
Yeah, that makes sense.
So,
Well, I think it's safe to say that we've accomplished our mission here. We've demystified the difference between discrete and continuous variables,
I think so.
explored their implications, and even touched on some of the nuances that often, trip people up.
It's been a pleasure delving into these concepts with you.
Likewise.
And I hope our listeners have gained a new appreciation for the importance of these seemingly simple, yet profoundly impactful building blocks of data.
And to our listeners, we encourage you to continue, exploring these ideas.
Yes.
Challenge yourself to think about the types of data you encounter in your daily life.
Absolutely.
Whether it's like the number of emails in your inbox or the temperature outside, consider how understanding the nature of those variables might shape your understanding of the information they convey.
Keep those minds engaged, and until next time, happy analyzing.